Hello, my project is in collaboration with Agilent and we will be looking at improving the evaporative light scattering detector, or ELSD for short, through experiments and modeling. To put it simply, the ELSD uses light scattering to measure analyte concentration. It does this through three main stages, where in the first stage it draws up the solution containing your substance of interest and nebulizes it, producing a fine spray. The second stage involves passing the spray through a heated tube where the solvent is evaporated off, leaving dry analyte particles which travel further down the tube. And in the final stage, these particles get to the detecting chamber where they scatter laser light, which is collected by some photodetectors and interpreted as a signal. Intuitively, the more analyte passes in front of the laser, the higher the ELSD signal will be. But the relationship isn't straightforward, and due to the complexity of this process, we can see from the graph on the left that the obtained signal is nonlinear in concentration. This can be corrected using a power law, and upon correction we can see from the graph on the right that the corrected peak area becomes linear in concentration. But again, due to this complexity, the process as a whole is not entirely understood. And so the project will have the following goals. We will characterize each stage of the ELSD process through a database of experiments and produce semi-empirical models to describe the dynamics of particles going through the device. The models for atomization, transport, and evaporation and light scattering will be linked through transfer functions, which will link inputs and outputs at each step. And so eventually we can create a simple 0 or 1D model for the whole system that will output an ELSD signal from some given initial inputs. Hopefully by doing this we'll increase the sensitivity of the device such that it may discriminate between similar analytes. This may also decrease the signal to noise ratio, and we may find the source or the physical explanation for the non-linear nature of the raw signal. If this simple model is a success, more complex 3D models or computational fluid dynamics may be implemented for device optimization. In order to validate our models, we'll use some key instruments such as droplet levitation techniques like optical tweezers in order to obtain droplet properties as a function of analyte concentration. We will also use a phase Doppler particle analyzer, or PDPA, to obtain particle distributions in space, particle velocity distributions, and particle size distributions. Thank you for listening.